In this video, we are going to look at proof by induction for sequences. So you should have already looked at proof by induction in the AS content for hopefully at least matrices and divisibility statements. So we're now going to do it for sequences. So what's going to happen in these questions is you're going to be given often a sequence defined by a recurrence relation, which we've got written here. So you've got the statement linking un and un plus 1. And then we're told that u1 is the first term equal to 2. So we're only going to focus on first order recurrence relations for now. Then the idea is you're going to be asked to prove that this closed form solution here is true for the sequence. Okay, so when it comes to the recurrence relation we're initially given, we're allowed to use that as much as we want. We can assume that is definitely true in all instances. However, our closed form solution here, this is the one we're going to have to prove is true. So our proof by induction starts in the usual way. We're going to start by doing our base case. So our base case is our first instance, our first domino essentially that we need to fall. Now we're trying to do this proof for all positive integers n. So you need to think, what is the first positive integer? Well, that is when n is equal to 1. So what we're going to consider is when n is equal to 1. And we are going to substitute that in to this statement here that we're trying to prove true. Okay, so I'm going to write u, and then in place of this n in the subscript, I'm going to put a 1 and say that's equal to, and then we're going to write our 4, and it's to the power of n subtract 1, so that's going to be 1 subtract 1. And then we've got this plus 1 over here, like that. Then we're going to simplify and calculate this. Do just show at least one step of working, even if you think you can get to the answer straight away. So I'm going to write 4 to the power of 0 plus 1. Then I'm going to go further and write that 4 to the power of 0 as 1. And if we add 1, we're going to get 2. Okay, and this is the expected result because in the recurrence relation, we're told that u1 should be equal to 2. So I can say, therefore, true for n equals 1. Okay, if we've got a value other than 2, we've done something incorrect and we need to recheck our working. Now we're going to move on to our inductive step. Okay, which I'm going to write over here on the right. So this is the step where we are going to assume that our closed form solution here is true for some positive integer that we're going to call k. Okay, so I'm going to write assume true for n equals k. And k must be a positive integer like n. So I'm going to say where k is a positive integer. Now, in terms of notation, I could have used to just speed that statement up. I could have said that k is an element of the natural numbers. Okay, that would be sufficient if you want to write that instead. Now, if we're assuming the statement is true for n equals k, essentially what I'm assuming is that if I take this statement here and I substitute k's in for the n's, that statement is true. So that's what I'm going to do next. I'm going to write therefore, and I'm going to write out that closed form solution, but with the n's replaced by k. So I would have uk is equal to 4, and then it's going to be the power of k minus 1, and then we've got the plus 1, like that. Okay, that's what we're assuming true. Now we have to do the hard part. We need to prove true in the next instance. So that is when n is going to be equal to k plus 1. Okay, so that's what I need to do next. Now, in order to do this and in order to assist, what I'm going to do is just write out a target statement. So you hope we'll be familiar with this from the matrix induction, okay, where you could potentially write out a statement that you're aiming for. Now, this is not part of the working. That's why I'm going to write it on the side. You do not get any marks for this. Technically, you don't even need to write it out. However, I do think it's quite useful. So my target statement, if this is going to be true for n equals k plus 1, I'm going to get this statement here, but with all the n's replaced with k plus 1's. So I would have u k plus 1 is equal to, and then we'd have 4, and I'm going to replace this n here with a k plus 1. So I'm just going to put it in brackets. And then we've got the subtract 1 in the power, and then we've got the plus 1 outside of our exponential term like that. So that is the statement I'm aiming for. That is what I should end up with on the page. However, I am just going to simplify it a little bit further just to see the more simple version. So that power would have 4, and we need to subtract 1 off the bracket, so it's just going to become power of k and then plus 1. Okay, so that is what I'm aiming for. If I can get this bottom line here, I know that that is equivalent to this top line here, okay, which will be my final line of working. So now we have to think about how we're actually going to get there. Now, in order to do this for sequences and proving closed form solutions are true, what you're going to start by doing is taking the recurrence relation, which we can assume true in all instances, okay, and I'm going to replace all of the n's with k's in my recurrence relation. So I would get u, and then it would be k plus 1 is equal to, and on the right hand side I'd have 4 lots of uk, and then we got the subtract 3. Okay, we can assume that's true because the recurrence relation is not what we're trying to prove, that's what we're initially given. Okay, we're allowed to use that as much as we want. Now what I'm going to do next is make use of my inductive assumption, so what I've got written here. Okay, so that's for UK. So what I'm going to do is I'm going to replace this UK with what I've circled there. So we'd still have UK plus 1, which is actually exactly what we want if we look at our target. So we're not going to touch that at all. And then I'm going to write 4, then open bracket, and I'm then going to write in this part here. Okay, 4 to the power of k minus 1 plus 1, close bracket, subtract 3, like that. Now, once I've done that, my next step is to simplify. So let's expand the brackets. We'd have 4 times 4 to the power of k minus 1, which I'm going to write like this initially. Then we've got the 4 multiplied by the positive 1, so that gives me plus 4. And then we got the subtract 3 outside the bracket like that. Now let's simplify. Now we've got a product and the base numbers are the same, therefore we can add the powers. The power of 4 here is 1, the power of 4 here is k minus 1. If we add them together, well, we're just going to get 4 to the power of k, which I like the look of because that's in my target statement. And then we got positive 4, subtract 3, so that is going to become positive 1. And as you can see, if I just carry down the u k plus 1, we've now got the bottom line of my target statement. So now I can rewrite this as the top line of my target statement, where it clearly shows that the n's have been replaced with k plus 1s. So I'm now going to write that in. It says u k plus 1 is equal to 4 to the power of, in brackets, k plus 1, and then subtract 1 plus 1. So we've now successfully finished the hardest part of the proof. Now the thing we're going to do next is write out those concluding statements that hopefully you should be used to. So we're going to say, therefore, true for n equals k plus 1, if true for n equals k. Because to do the proof for n equals k plus 1, I started by assuming it was true for n equals k. Then I can say, also true for our base case, so also true for n equals 1, which was my base case over here. Then I can say, therefore, un is equal to, and I'm going to write out what I was trying to prove, so the 4 to the power of n minus 1 plus 1. So therefore, un is equal to 4 to the power of n minus 1 plus 1 for all positive integers n, because that's what I was asked to prove for. And I'm just going to write by induction, okay, just to list out and mention the type of proof that I'm doing here. And that would be our complete proof by induction for sequences.